since I think we may have everyone who's here to join us. We've got our formative assessment in icon to do, as well as the remainder of lecture 1. I was saying one announcement, I put up an announcement in icon, but in case you haven't seen it yet, one of you asked the library to buy our class textbook. I don't know who it was, but thank you, because I didn't know that was a thing I could ask for. So the book is now available on electronic form through the library. I don't believe there is a restriction in how many people can look at it at the same time. There is a restriction of how many times it can be opened, but once that restriction is met, they will apply to get more looks. So it's some kind of metering system, but the library assured me that they will pay for more looks. So you are able to access the textbook through the library. That information has been added to the syllabus, where the reference for the textbook is given both in the paper version as well as the online version. Yes, don't thank me, thank one of you. So if anybody wants to step up and claim, thank you for going to the trouble of contacting the library. I had no idea that that was allowed, but as soon as I found that out, I went ahead and asked for the book from my other class as well. That one, unfortunately, is only available to one person at a time, making it a little bit less useful. So, share the
Lisa,
screen. Yeah.
I don't know if this is a negative thing, but I also have you can find the PDF and it's downloadable on the web of the book.
Okay.
So,
all right. So that information, if you'd like to DM your classmate about that information, I did not hear that. I'm not privy to any such exchanges. But at the same time, I know grad students have no money, and I will not say anything about that. So yes, that is also true for the book for my other class I learned. So I think if you dig deep enough, you can find many things on the internet, which is a nice thing. Let me see here. What was I looking at? Oh, yes. I wanted to show you this. So the link to the textbook through our library is down here on this page. And I also wanted to show you something that is somewhat on topic, but a little bit different. So the other day I got an email from one of our advanced graduate students asking for a letter of recommendation for a postdoc that he was applying for at the University of Hong Kong. And he sent me the job ad so that I would know what the position was. And so I went and looked at it. This is the position. Can everyone see what I'm looking at here? Yes, let me get the transcript going before I forget to do that, so that you can watch my words if you are so inclined. You can hide them as well, which is what I'm inclined to do. And so I looked at this, and he's applying for a postdoctoral fellowship, and I get to the second paragraph here, and lo and behold, experience in analyzing data using R, Stata, SAS, or other statistical packages. So I'm not making this stuff up, right? These are skills that employers want. So I thought it was a nice coincidence that the 3 packages that I'm promoting in this class are the ones that were listed explicitly. So just think how good of a candidate you could be if you knew all of them as opposed to just 1 or 2. So provide some concrete incentive to be able to work with software. So we have a formative assessment to go over, and I realized after class that we hadn't gotten as far as I had initially planned with respect to questions 2 and 3, but that's okay. We will go over the answers today as part of class, and so once we hit that point in the lecture, I will segue back into this. But the first question that I asked about was, what is the difference between a categorical variable and a quantitative variable? Anybody want to volunteer what they wrote down? You can type it in the chat window if you're feeling shy, or you can just unmute yourself and volunteer.
Categorical variable is where the numbers are labels.
Yes.
And quantitative is where numbers are numbers.
Yes, indeed. That's exactly it. Can you think of any subtypes? Kinds of categorical variables, for instance.
Frequency. I put down frequency, proportion, and percentage.
Those are ways of indexing how many you have in each category. So it's adjacent. In terms of the types of labeling systems, though, that we can have, that's what I was going for.
I put binary, nominal, and ordinal.
Yeah, those are the three that I used. Any others that you can think of off the top of your head, terms that you would have heard perhaps elsewhere?
Like dichotomous being the same as whatever the other one was. Dichotomous binary,
Yep, dichotomous, binary. Those are synonyms for a categorical variable that has only two possibilities. Yep. Got a few answers in the chat here that I'm looking at. Thumbs up to those as well. Can you think of examples from your worlds in terms of research or things that you care about that would involve categorical variables? Census data? Sure. What else?
gender, identified race,
Yep.
hair color. Well, that was not, I guess, hair color.
It would be assessed that way, right? You could ask somebody, what color hair do you have? And they could say blonde or brown or black. Although it is sort of a sliding scale. Like, how blonde do you want to be is a different question, right? It's between you and your hairdresser, perhaps. Relationship status, yep, there's another one. And so then in terms of how to summarize them, that answer was already given. We want to know the frequency of each category. You take the frequency and divide it by the total, that gets you proportion. Multiply that proportion by 100, you get percentage. So you don't have to worry about anything else really other than reporting either proportion or percentage of people along with the total. And that's all you would need to describe a variable like that. Good. Quantitative variables. Any examples come to mind for those? Age, yeah, that's a good one. Years of education. Test scores. Things like that. Weight, yep. Add height to that list. Temperature. Celsius and/or Fahrenheit. There's a lot of variables that end up being quantitative. The key distinction, though, is that you have to tell your program that you're working with whether something is a number or not a number. You would deal with those very differently in terms of how they would enter the model as a variable to be included. So the ones then we're talking about quantitative variables and how those would be described, and that was the part that we hadn't gotten yet. So we can translate over back into the lecture slides for that one. Let me close these windows so the computer doesn't overheat. So any questions on that so far? Or clarifications? No? We're good? Okay. So jumping back in, then we were talking about how one might summarize quantitative variables. Let's pick up on slide 14 of lecture 1. This is where we are. I think we looked at this last time. So this is an example of a frequency table for a quantitative variable, which is useful if you want to know how many people have each distinct value, but it is not useful if you want to be able to summarize the variable more generally, because these distinct values don't really convey how related they are to each other, how close they are numerically. Likewise, a frequency plot has the same problem. It would not be useful for most quantitative variables where you might have a bunch of different possible values. So what we might do instead is a plot that goes by a different name, but it would look similar. Reminder to record. If I haven't yet, I am, but thank you for reminding me. Because you know what happens if I forget to hit the record button? I get to re-give this lecture to no one in my basement. That is what happens. I have done that at least 4 or 5 times in this Zoom world, and I gotta tell you, it's not nearly as enjoyable. I very much like talking to people instead of myself. So we want to make a better picture, which is known as a histogram. Here is how we would tell the software to make us a better picture of a quantitative variable in each program. So in SAS, for instance, we have Proc Univariate. In Stata, it's the same histogram command that we had before for a frequency plot, and it's the command hist in R. So the key difference of this kind of plot is that it bins quantitative values together. So it essentially rounds them into chunks, and then it displays the frequency of each chunk. So it's a much better way to describe the general tendency in terms of the distances between the numbers. The only catch is that each program has its own set of rules for how it wants to bin the values together to round them into the bars. And so even if you try to make them look the same across programs, there may be slight differences. And actually, I found that in this case. So for example, if I'm working with our variable income, which is in $1,000 units, so it ranges from a low of, let me go back to the previous slide here. Yeah, the low is 0.245, so somebody who reported an income of $245, up to a high of $68,600. So that's the range of this variable. Oh yes, sorry Kuhn, I didn't see you. The other TA here is here to greet you, and I forgot about that. So can you unmute yourself and say hello? There you are.
Oh, good. Hi, everyone. My name is Kuhn. I'm your pay TA.
Yes.
Yes.
He's not volunteering. He's getting actual money.
Yes. And then I know some of you from the previous introduction statistics class I have TA for last semester. And CP students. I'm also a CP doctoral student. So I know some of you. I just want to say hi and then welcome to my office hour if you have any questions. Currently, I'm using R package to solve the assignment and then other statistic questions. So if you have any questions in using R, please come to my office hour. I will help the questions and related questions. Yeah, that's what I'm trying to say to you.
And do you want to remind them when your office hours are?
Yes, my office hour is on Monday and Tuesday. Monday is 8 to 9:30, and afternoon 12 to 3. And Tuesday is also morning 8 to 9:30, I believe. And my Zoom link is posted in this class website,
Yes.
so you can find my link there.
Yes, so it's handy that you're having office hours on Mondays, since Monday night is when most of the assignments are planned to be due. So if you have any last minute questions, you can email me, and you can also stop by his Zoom room. So sorry to have forgotten that part, but thank you for letting me know.
It's all good.
Okay, so
Nice
he's got
meeting
another
you.
meeting. He's got a jet, right?
Yeah.
Okay.
And enjoy the class. Bye.
Bye-bye. All right. So, anywho, looking at a quantitative variable and how one would depict that graphically, if you know the range of your variable, then you can make a decent guess as to what would be effective in terms of bins. So we have a question about binning. Does binning quantitative data turn it into categorical data? Temporarily. So there's a distinction between what you would do to visualize your data versus what you would do to analyze your data. To analyze your data, I would never have you round a quantitative variable into bins. Because if you collected it at a much more fine-grained level of detail, if you round it into bins, then you are introducing measurement error, essentially, and you don't want to do that. There are maybe cases in which that might be necessary, but by and large, you want to keep it quantitative if you collected it that way. The same thing goes in terms of making decisions about how to collect information. If you want to eventually look at something like whether somebody is in, say, elementary school, junior high, or high school, right? Like if you have a research question that is phrased that way, I would still ask your students what grade they're in, because you can always take what grade they're in and turn it into elementary versus junior high versus high school. But if you ask them elementary, you can't go back and figure out whether it's first grade or sixth grade. And I got to tell you, I'm pretty sure there's a big difference between a first grader and a sixth grader being the parent of a first grader currently. There's a very big difference between a 6-year-old and a 3-year-old, I have learned, for the same thing. So I would collect the information with as much fine-grained detail as you believe someone is capable of giving you, and then you can decide to cut it up or bin it later if you want to or need to, although most of the time you don't want to do that. What I'm talking about is just sort of temporarily binning it to make a visual display that is more useful. That's all. Thanks for the question. So to make a useful display then, given that I know that the range is from 0 to about 70, I'm going to pick bins of 5. So $500 increments. That way I have enough bins, but not so many. The way that I tell SAS that is with this midpoints option here. And it means exactly what you would think it means based on the words. Start at 0, go to 70 in increments of 5. In other programs, you don't phrase it that way. In Stata, for instance, I'm telling it that I want a histogram for the column called income. I want it in percent. With 5 is the correspondence of by 5. And then start 0 is the correspondence of this 0. But there's no direct way to tell it where to end. It figures that out for you. In R, the hist option, first it wants to know what variable. So we've got the name of the data and the variable tied together in R with the $sign separating the name of the data from the name of the variable. Frequency equals false. Can you guess what that means? Any guesses?
Not looking for it?
I'm not looking for frequency. What would be the alternative for the y-axis? If I don't want to know the frequency of the bins, I might want to know the percent instead. So frequency equals false means give me percentages. I know. Breaks equals 15. That's how many bins I wanted. It took me a while to figure out that correspondence. So each is a little bit different in how you ask for things. The labeling conventions are used that are already in the data in SAS and in Stata, and in R. R doesn't do variable labels in the same way, and so I had to add them here. But that's what YLab and XLab means. It stands for labels. So let's see what we end up with across programs. Here's the 3 histograms that showed up when I ran this in each of the packages. And even though I tried to make them look the same as possible, they're not exactly the same. So this is to say this is a descriptive sort of heuristic level thing. It's not like hard and fast rule. But the point that these pictures are making, I think, is the same across the packages. There are more people who make less money than there are people who make more money. So there's sort of a pileup of people at the low end of the distribution, and there's relatively few cases at the high end. So that is conveyed, I think, in each of these cases. So what would we want to summarize then in terms of describing a quantitative variable? So this is question 2 in your first formative assessment. What are the 3 salient features? And I guarantee you've heard this before at some point in your life. So our purpose in going over it is not necessarily to give you new information, but it is also to give you new notation to go with this information in terms of how you would represent these ideas in formula, as well as how you would ask the software to spit this out for you, because that's the new part. So one salient feature, central tendency. What does the average person look like is kind of the idea here. And all 3 of these start with the letter M, but when you see an abbreviation of M, In a result section, for instance, or in a table, it means mean. So M is reserved as a keyword for mean. The mean, of course, the arithmetic average, and yes, there are other kinds, which is why I throw that word. It's exactly what you think it is. Median is the middlest value if it's ordered from most to least, and mode is the most frequent value. In terms of modeling this stuff, mode never shows up in the context of models. It shows up in estimation, but it doesn't show up in terms of the model. Almost everything that we do in statistics is about the mean. Median sometimes gets used in models, but not very frequently, and not in this class. So mean is going to be the big one to focus on in this case. But beyond the mean, we also need to know about the variable's dispersion. So how different are people on this variable from each other? So I can give you a ready example from my life as to why this might matter. So you've heard me talk about my son Hugh. He's 6, almost 7 years old. You met him potentially last week when he came to say hello. I also have a stepdaughter. And if you put the two of the children together, the average age of my children is 11. So if you think about the average age of 11, you might think, well, like a 10-year-old and a 12-year-old, that would describe my brother's family. My nieces are 10 and 12. But in my family, it would be a 7-year-old and a 15-year-old. And that's a very different parenting experience of a 15-year-old and a 7-year-old than it is to have, say, a 12-year-old and a 10-year-old. So just knowing that the average age is 11 is not really enough to convey what this is about. So conveying dispersion then can happen basically in 2 ways. Standard deviation and variance in one corner, and interquartile range in the other. And standard deviation tells you, on average, how far off from the mean any given observation is expected to be. The square of that is variance, and I'll show you the formulas for that in just a second. So given one of these 2 values, you can get the other. You don't need to give somebody both. They're redundant in that sense. SD is a very common abbreviation for standard deviation, and it's a more intuitive way, I think, of describing dispersion. Variance is the squared units, and that is more common in describing model results. How much variability in the outcome you've predicted with your model, for instance, is how people talk about it, rather than in the unsquared metric, which is standard deviation. Interquartile range is another thing entirely. That is related to the median. So the interquartile range is the distance from the 25th percentile of the data to the 75th percentile, where the 50th percentile is the median. So the middlest value at 50% is median. 75 to 25 then describes the width. And it does so more effectively for distributions in which there are extreme cases. So distributions that have skewness, we'll show a couple of those in just a moment. And then the third one, skewness, is asymmetry. So is the distribution symmetric? So there's as many people on one side of the mean as the other? Or is there sort of a pile on one side and then fewer people on the other? And that is something that doesn't get taken into account in models directly, but it's something that should inform how you think about a variable, particularly if you're going to predict it as an outcome. So it's something that you would want to look at, but not necessarily report. There are things that you can report for skewed data, though, that you might not think about reporting for symmetric data. So let me show you a couple pictures of those. Okay, so to illustrate then standard deviation and variance. Both of these histograms were created using fake data that I made up, where the mean is 100 in both of these. So the middle value is 100 in both of these pictures. The difference between them is in the standard deviation. So in the picture on the left, the average person who contributed to this histogram is off by 10 units from the mean. 10 squared gives you your variance of 100. In the picture on the right, the average person is off by 15 units. 15 squared is 225, gives you your variance. So the picture on the right is more spread out. People are more different from each other in this variable on the right side than they are on the left side. Another way to think about it is that the mean is potentially more useful for the distribution on the left. People are closer to it, whereas the distribution on the right, any one person is not as likely to have the mean score. Skewness, then. Skewness dictates how your measures of central tendency are going to be the same or different. So skewness is somewhat confusing in the way that it's named because it's backwards from how you would think about it. The direction of the skew is the direction where the tail is heading. So this distribution here on the left is a positively skewed distribution because the lower side, the negative side, has most of the data, and the higher side has less data, fewer cases. A symmetric distribution here is in the middle, so equal on both sides more or less, and then the opposite, negative skew, is on the right side here, where most of the people are on the high end, less on this lower negative end. And the other thing that I want to point out is that the measures of central tendency diverge in skewed data. So if you have a positively skewed data set, something like home prices, for instance, when people talk about home prices in a given city, it's the median home price that is often given, and it's because home prices are a skewed distribution in most cases. A question about that: in the interquartile range, is the 50th percentile not also the mean? Nope, it's the median. If you had a symmetric distribution like the middle one, mean and median and mode are going to collapse onto about the same value. So the middle is the middle. If you have a skewed distribution, middle is something that you have to define explicitly. So in a positively skewed distribution, the reason that people report the median instead is because the mean is affected by this tail coming out here. The mean is dragged away from the bulk of the data by outlying observations. So what is the cheapest house that you could possibly buy? A tiny house, probably, right? Something that's not zero, but low.
$1.
$1, yeah.
No, 1 cent would be the cheapest, right?
At 1 cent, yeah, in theory. Like perhaps you're going through a very contentious divorce and you have to split the proceeds with your ex-spouse and you sell your house for 1 cent just to make them mad. That is one of the plots in, what is it, First Wives Club, by the way. That's not my own joke, that's theirs. But something like that, right, 1 cent. What's the most a house could cost? I saw this on Colbert the other day. There's a house that is in California that set a record. $285 million. It has over 100,000 square feet. So somewhere between a penny and $285 million, right, is how much housing is in America. But if I were to try and report like the mean house price, that 285 million is going to drag that mean out to where it's not really a good index of middle anymore. And that's why median tends to be favored in skewed distributions, because it's closer to where the data is in that case. Okay, good. And mode will be even further to the left here. So this kind of skewness can also result from what is known as a floor effect. If you give a class a really hard exam and most of the people don't do well on it, this is what you get for a distribution, right? A pile of people who did not very well and fewer people who did well. In this class, which of these distributions do you think I want to look at in your grades at the end of the semester? Negative skew, yeah. Ideally, actually, I would like to see what is known as a degenerate distribution. Degenerate means constant. I would like a distribution that is a straight line filled with A's. That is what I would like to see. But this would be a nice second place. Negative skew often results from boundaries at the upper end or a ceiling effect, for instance. If everybody gets 100 on the test, the bulk of the distribution is high over here, and then we have fewer people heading out this way. So in this case, the mean is further down towards the tail of the data in the opposite direction. So cough, cough, first homework question will be about comparing means and medians and what you can learn about the shape of a variable from that. So in practice, skewness is often caused by boundaries in the variable that's being measured. And that means that it's not necessarily something that you can fix by collecting data differently. The only way that one could eliminate a negative skew would be to somehow extend the scale of what you're measuring further over. In a testing context, it would mean like adding harder questions. Likewise, in a testing context with a floor effect down here, you'd have to add easier questions that more people could get a chance to have correct. That would help spread out that distribution. So it's just good to be aware of these sorts of distributions in terms of how you would think about the data, how you would describe the data. Mean and standard deviation are just fine if you have a distribution that's symmetric like this. But if you have something that's skewed, you might also add in median and interquartile range as additional information. All right. Questions on anything so far? Okay, I'm watching the chat window just in case. All right, away we go. So notation time. This slide is my apology to you because I'm going to, in some parts, ignore everything you've probably been taught about notation. Because once you leave the world of mean and variance, the distinction between sample versus population notation starts to break down. So the way that at least I learned it, and in the introductory stats textbooks that I've seen, they make a big deal out of this, and they talk about, well, if you have the population that you think exists and you're trying to make conclusions about it, then you have parameters, but then in the data that you have, which is a sample from the population, a characteristic of that sample is a statistic, and you're trying to get statistics to mimic what the parameters should be. And under that notational system, everything that refers to a population idea as a hypothetical construct, because you almost never have the population, is supposed to use Greek letters, aka what we now know of as the pandemic alphabet. Millions of Americans have started learning Greek letters against their will because we talk about the Delta variant and the Omicron variant. And they skipped a couple letters that are common last names in certain cultures. But next, I think, is the Theta variant, maybe. Also, in hurricane season, when we run out of letters, they switch to the Greek alphabet. And then you get with Hurricane Alpha, Hurricane Beta, Hurricane Chi, and all that kind of stuff. So population notation traditionally uses Greek letters, and sample notation uses the letters that we're used to. That distinction starts to fall apart very quickly when we're talking about models. So I will end up with sort of a hodgepodge of both by the end of the semester, but I'm presenting it here because I'm guessing you will have seen it, and I want to try and be consistent with the way that you have started learning these things. So if I want to use a notational system, so this is a new set of language, essentially, to describe how one would compute the mean for a quantitative variable, then I would need to use the following terms. So first thing here, y sub I with a subscript. That refers to an outcome variable. I will use y for outcomes and x for predictors consistently throughout this class. The key thing here is what the little I represents. Anytime you see an I, that means that it is a variable that varies across persons. So it is a column in your data set that we are referring to if you see a little I on there. Big N, capital N, sample size. Almost universally, you will see it as sample size. If people are describing subgroups within a sample, like I have this many people in the control group and this many people in the treatment group, big N would be for everybody all together. And then to describe how many people are in each subgroup, you'd have like little n for the number in the control group and little n for the number in the treatment group. That is a very universal convention. So you'll see capital N sprinkled throughout my slides. Every time you see it, it means sample size for everybody. The last person in the sample, if I were to list everybody in a series, I'm using y sub n to indicate that. And then the sample mean that you end up with after you're all done computing the mean is y bar. So the thing across the top means mean. And note that there is no I on y bar because y bar is not a variable, it is a constant. The one sample mean describes the mean for everybody. So using this notational system, this is how I would describe the computation of a mean. Y bar equals all the individual y's up to the last person divided by n, and that add everybody up is capital sigma. So when you see capital sigma, think add, starting at the bottom thing and up to the top. So we're adding everybody up, starting at I equals 1, all the way up to n. What are we adding? Each individual y, divide by n. Another way to say this is that in computing the sample mean, what we're trying to do is estimate what the population mean could be. And so the idea that there is some giant mean out there that we don't have access to, but we're doing our best to try and figure out what it is with just the data we've collected, that population mean is referred to as mu, which is this U looking thing here. That's a Greek letter. And what we have in our sample is y bar. So we never know what mu is in the vast majority of cases, but that doesn't stop us from trying to approximate it by collecting a sample of data and calculating the mean for them. Okay, does this look familiar? Maybe? Yeah. Now keep in mind, am I going to ask you to calculate any means in this class? No. You're going to do it in Stata or SAS or R. Could you do this in Excel? Yes. Could you do this with a calculator? Yes. But there are many things that Excel and calculators are going to be painful or just wrong to do. So the purpose of reintroducing this stuff, familiar territory, is to show you how to get the software to give it to you. That's what we're really trying to get after here. So that's my mean. Here's variance. So now we're heading into the third question on your formative assessment. What's the relationship between variance and standard deviation? Standard deviation is in unsquared terms and it's more intuitive. But to get to it, you got to have variance first. So variance is a way to describe the dispersion of the people in the sample around the mean. It is used, the symbol used to describe it for a sample is traditionally S squared, and the squared is because it's in squared units. Whereas what we're trying to estimate is sigma squared, and I have a little e on here to foreshadow that it's going to have an e once we get into models and we talk about residuals, which is uses an e for an abbreviation. How we calculate variance? It's y for each person minus the sample mean. So how far off are you from the sample mean? Now, if we just left it there and added up those deviations, those offnesses, what would happen? If I just did y minus the mean for each case and summed up those deviations, what would I end up with? Zero. Yeah. Because the positive and negatives would cancel out. So to prevent positive and negative deviations from canceling, we square them. So that's why we have to take the deviations and square them. So we subtract the mean from each value, square that result, then add them up. That's where the term sum of squares that you've probably heard before comes from. We are summing the squared deviations, offnesses, as it were. summing them over all the people, starting at 1 up to n, and then dividing by n minus 1. So it used to be n for the mean, it's n minus 1 now. The reason for that, we have to have the mean in the first place to do this. So the n minus 1 is a reflection of the fact that we already had to know one quantity to get this to work. Later on in the course, that idea of how many things we had to know is going to be called denominator degrees of freedom. And it's literally the denominator of this equation is where the term comes from. So variance is squared deviations. And if you tell somebody, yeah, the sample has a variance of 100, they'll be like, is that a lot? Because squared units are not intuitive. So to convey something in a metric that is more interpretable, we take the square root, we unsquare it, and that gets us back to standard deviation. So if I told you, well, the variance is 100, but that means the standard deviation is 10, now we're cooking with gas. Because 10 means, okay, so that's how far off on average any one person is from the mean. So how good the mean is at capturing sort of an individual tendency, you have to know the standard deviation to make an assessment of that. If the standard deviation were 1, then everybody's right around the mean real close. If the standard deviation is 10, people are more spread out. So we have to do variance first, take the square root of it to get to standard deviation. But you only need one or the other because you can always go back and forth. Okay, any questions on that? All right, moving on. Skewness, if you ever wanted to compute it, is the same idea except that it's to the third power. So if it's a positive number, then you end up with positive skewness. And if it's a negative number, you end up with negative skewness. And if it's 0, then it's a symmetric distribution. So in the example histogram that I had created, I have 3 values here for central tendency, and I've tried to map those onto where they are in the picture. So in terms of income, the mean income for this sample is $17,000, $17,310 to be specific, because this is in $1,000 units. That's like in this bin right here. The median is 13. So the middle value is less. That means the mean is being dragged out by people who make a lot more money. So which type of distribution is this? And feel free to read from the slide. I like to put Easter eggs in here to encourage class participation. What kind of skewness is this?
Positive.
That it is, positive skewness. And I know that because the median is less than the mean. The mean is being dragged out by the positive skewness, the tail cases that are fewer than the rest. Mode is actually 22 in this case, so that was the most frequent category. In terms of the dispersion, the variance is 190. Okay, thanks. I don't know what to do with that information. If I take the square root, the standard deviation is just under 14. Okay, so on average, people are off from the mean by $14,000. Okay, I can work with that. The interquartile range, the 75th percentile is 22 and some change, 25th is 7 and some change, and that gives us this here. So in terms of describing a quantitative variable, what you would want to have is the minimum and the maximum, often known as the range, at least the mean and the standard deviation. If you have a skewed variable, you might want to throw in median and interquartile range in addition to that. You might want to make a picture. This is called a box plot, because there's a box, and the box describes most of the cases. So I made this one in SAS. Each program does things a little bit differently, but this is a way to also show a symmetric distribution in a different way than the histogram, but it kind of gets at the same idea. Nowadays, there's cooler versions of this that are known as Violin Plots. There's all kinds of cool plots. So I didn't know what a violin plot was until reviewer 3 insisted that we needed one in a paper that I was helping with. And so I asked the Google, what is a violin plot? And found some code to make one. And it's basically this with a different shape and a little bit more information and more color. So color is, by the way, very nice when you're presenting your graphics in a talk, not allowed in most journals. So all that lovely color coding scheme that you might use to make your plots look pretty go to waste, sadly enough. Kurtosis is another thing you may have heard about. You can ignore it. It has to do with flatness, and it's almost impossible in practice to tell the difference between kurtosis and variance. And gun to my head, I still don't know which of these is which without the mnemonic that platykurtic means flattykurtic. That's it. So kurtosis is to the 4th power, by the way. It has to do with squishiness of a distribution. In practice, this information is not going to be helpful to you, so you can pretend like I never talked about it. All right, so the more important thing, how do I make my software give me all of this stuff? In SAS, first, Proc Univariate. So this is the same routine that we use to make a histogram. Now I'm highlighting the rest of the output that will get spit out for you in addition to that plot. So Proc Univariate data equals where it is, what the name of it is, which variables you want it for. So if you'd like it for more than one variable, you can list more than one on that var statement. Var stands for variable. They would all go before the semicolon. And then run, which is required to close the proc. So think of it like a sandwich. Like proc whatever is the bread, stuff is the middle of the sandwich, and then the other piece of bread is the run. So they go together as a set like that. And all of this stuff pops out. So I've bolded the things that we've talked about: sample size, mean, standard deviation, skewness. It prints out a whole bunch of stuff. Here's all of my medians and quantiles and things like that. And if you're looking at all these numbers and going, oh my God, this is too much, can I just get a mean? Yes, you can. It's a different routine. So proc means gives you the cliff notes. Do we still know what cliff notes in, or am I that old? The cliff notes still a thing? Okay, so back in high school, when I was no way going to understand Shakespeare just by reading it, I got the cliff notes. Because I still don't understand Shakespeare. I would read it and I would have no idea what I just read, and then I would read the cliff notes and go, okay, got it. And then I could participate in the rest of my English class. This is the cliff notes version. So proc means, by default, will spit out the sample size, the mean, the standard deviation, and the minimum and the maximum. Just the bare bones that you need to describe a variable. I also asked it to give you variance so that you could see that be repeated across itself. This var right here on the first line and this var right here on the second line are not the same. I know. This one on the first line means variance, as an extra piece of output that I would like it to give me. This var on the second line means variable, as in which columns of your data set would you like this information for. Job security, my friends. All right, any questions on this stuff in SAS? All right, Stata folks, you're up next. 3 words. Summarize. What would you like to summarize? The variable called income. Do you want to know everything we got? Yes, comma, detail. And it spits out all this stuff. So it's in a slightly different order, but most of the information is the same. We've got quantiles or percentiles as they're known, sample size, mean, standard deviation, variance, skewness, kurtosis, etc. And yes, if you want a shorter version of this, if you take off the detail and just have summarize, you get the bare bones. So in your homework, once we start having homework that's not about the syllabus, I will ask you sometimes for standard deviation and variance separately. I'm looking to make sure that you understand the difference and that you understand how they're related. But if you try to compute standard deviation by squaring it, your answer will not be as precise as if you ask the program to do so, because the program is maintaining all of this level of precision of the number. So you could end up with a wrong answer for variance due to rounding error, is what I'm saying. So in general, if you find yourself getting Excel or a calculator out to answer one of my questions, stop. Let the computer do it because it will be more accurate. Question from the group, are we supposed to have it downloaded already, or are we going to demonstrate how to get those? So I am going to make videos on how to get to each of those. R is the only one that you could possibly download for free onto your own machine. Stata and SAS you have access to through what is known as the University Virtual Desktop. So that is a Windows interface that you have to log into, and then it looks like a regular Windows desktop. Notably, if you are a Mac user, you can still use it. There's a little bit of a hiccup in telling it where your files are sometimes, but you can use it regardless of your operating system. So I have not yet made the videos because I have not yet needed you to do anything with the software yet. We're just sort of starting to wade our way into that. But I will have videos to demonstrate how to get to this information and actually make it get spit out for you. If you want to get ahead and you intend to use R, you could go ahead and install that now. So you would install R first and then RStudio second, and links to those are provided on the syllabus. Okay, so summarize income, bare bones, variance is provided if you add detail. That's the main point for this slide. All right, and R. Okay, so in most cases with R, I am going to try to stick to what is known as base R, meaning just the functions that it came installed with. However, people have written their own routines to do things in a more convenient fashion, and this is going to be one of them. So there is a package in R that is called Psych. And for those of you who've worked with R before, do not worry about the packages. In the code that I give you for everything, it is going to include lines that check to whether you have that package already, and if not, it will download it and load it up for you. So you don't have to keep track of which package has what thing. That's my job. But I'm telling you, this is a separate package that is called Psych that was written by a psychologist, Bill Revell at Northwestern, to mimic the capabilities of other programs that spit out information in a very condensed format. So describe is the function here. The variable that we want described is here. And I'm asking it to add quantiles to match what is given to the other programs and to add the interquartile range. So if I just had this much that's inside the parentheses, then I get these results. Adding to it though, I'm putting that function inside another function for printing so that I control the level of precision of the output. So I wanted 4 digits total for each of the numbers, and so that extra piece here allowed me to have greater precision. Otherwise, it defaults to something with much less precision. So this is a whole laundry list of stuff. Sample size, mean, standard deviation, median, trimmed mean, I don't remember how that's calculated, you can ignore it. Mode something, I think. Mean absolute deviation, maybe. I don't know what that is. Don't care. Minimum, maximum, range. Okay, that's the difference between min and max. That's useful. Skewness, kurtosis, standard error of the mean we'll talk about next time. IQR, and then the 3 things. So what's not here that we might want? What happens if we put false for IQR? You don't get it. So it's adding a piece of information to the output to put true in this case. What's not here that I might ask you about? Variance, yeah. So it turns out you can just ask for that. So in base R, they have all these little functions that give you just the thing that you're looking for. So to get the variance of a variable, the function is var, and it spits out that number. Likewise, if all you want is a mean, there's a function called mean. If all you want is standard deviation, there's a function called SD. And so if you run mean, the mean pops out as the first number, SD pops out as the second. And I want to point out that you can put more than one command on a line in R if you separate them by a semicolon. They don't all have to be stacked on separate rows.
Can
So
I
this
ask a
one's not
quick
too bad.
question?
Yes, please.
Why do we need the variance if we have the standard deviation already? Because isn't the variance just like there to help us figure out the standard deviation?
Yes, it is. However, in certain circumstances, you would want to report the variance as opposed to the standard deviation. And I want to show you how to get that information out of the software so that you don't end up with rounding errors because you took the standard deviation to say 2 digits and squared it.
Got it. Thank
Yeah.
you.
Yeah, so this is more like to make sure that you get the correct answers for the homework to the level of precision that I'm asking for, as opposed to like in life. That's actually a reviewer theory kind of question. I see that variances were not provided in table 1, but you reported standard deviations. If the reviewer wants to throw a fit about it, add a variance column. Get your paper published. I just want you to have access to everything. That's all. Question?
Sorry, I have one question about the SAS syntax. So in the previous page in the SAS,
Yes.
yes, we have data equals work dot example 1, and there is NDEC equals 3.
Oh,
What
this
does it
thing.
mean?
Yes. That stands for number of decimals.
Okay.
Yeah. So do you see how like this gives you a whole bunch of numbers and it can look messy? So if you want to cut down on the level of precision that is reported, in proc means it allows you to do so.
Thank you. And then do we need to write down and mean, standard deviation, variation, even though we have proc means?
So if you don't write any of these blue letters right here, if you stop it after the 3, what you will get is n, mean, standard deviation, min, and max. So the reason that I wrote all of these out is to add variance to the list. But if you just type variance, rather than adding it to what's already there, it thinks that's all you want. So
Okay,
if you
got it.
want to mess with its prescribed list, you got to list everything you want. Otherwise, like if you just list one thing, you get that one thing.
Okay, thank you.
Sure. Other questions? All right. So this is not so bad, right? Just little snippets of code to do basic things. That's where we're at. What about categorical variables? So for binary variables, for instance, most of the time binary variables are stored as 0 and 1, and that's for good reason, because that is how they would end up being used in a model. So if you are going to do any kind of data entry, or if say you're setting up a Qualtrics survey and you want to ask a yes/no question, make 0 no and make 1 yes. Just do it that way. Save yourself the hassle, because eventually you're going to have to change how it's coded to 0, 1. And as non-intuitive as it may seem, you can compute a mean for a binary variable and have that number make sense. So for instance, if you have mortality as an outcome, or dead equals 1, the mean for that variable would tell you the proportion of people who died. That would be death rate. That's perfectly fine to do, even though it's a categorical variable, because there's only one difference between the two numbers. For nominal variables, though, if you have 3 or more categories and the categories are unordered, in that case, even though you can ask for things like mean and standard deviation, it makes 0 sense to do so. So for example, if I have marital status here, the numbers that go with these labels are completely arbitrary. I could have put them in any order. 1 does not have any meaning other than just a separate type of category. But if I feed this variable into SAS and it's stored as 1, 2, 3, 4, 5 as the possibility, SAS doesn't know that these aren't really numbers. So it'll happily give me a mean, and it will tell me the mean is 2.7. That number doesn't mean anything. For ordinal variables, this is where it gets a little iffy. So for instance, another variable in the same data set is self-reported happiness. And it is 1 category for unhappy, 2 was neither happy nor unhappy, 3 was fairly happy, 4 was very happy, and 5 was completely happy, otherwise known as people who are lying. Are these numbers? Not really. Not in the sense that like there's amounts, like it's not like temperature. But if I told you the mean is 3.5, and that means that on average people are somewhere between fairly and very happy, that seems okay-ish. So this is where there's kind of a gray area in what people do with these variables. If you treat it as a number, you are implicitly making the assumption that the differences between categories are equal. That the shift from a 1 to a 2 is the same amount of whatever you're measuring as a shift from 2 to 3, from 3 to 4, from 4 to 5. If this is an outcome variable, that is potentially problematic because the outcome could potentially be predicted beyond just the scale that you have here. If it's a predictor, it's actually an empirical question as to whether you can think about it as a number, meaning that you have a linear relationship, or whether it's not a number, meaning you should have like a series of distances instead. So later in the course, I'll show you how to actually answer that question using the data that you have. By the way, this is pronounced Likert, not Likert. It's somebody's name that is associated with this type of scaling. All right. For categorical variables, you do not need to worry about standard deviation or variance. In binary variables, there is no such thing as variance that is separate from the mean. How you compute a variance in a binary variable is the proportion of cases that have a 1 times the proportion of cases that have a 0. So if you have a binary variable with the 50-50 split, its variance is 0.25, the end. If you have a variable where 40% is 0 and 60% is 1, its variance is 0.24, the end. So all you need to know is the proportion of people that have a 1, because then you know the proportion of people that have a 0 is the rest. Then you know the variance, actually then you know the skewness. The same is true in terms of categorical variables for nominal variables. For each pair, you could work out what the variance has to be. So point of the story is all you need to know is the proportion in each category. That's enough. You don't have to worry about dispersion for categorical variables. Wrapping up. Almost. I had a couple slides about data because we had some questions about that. But this is everything that I said. Any questions on anything that we've talked about thus far? We're good so far? Good as we're going to be at 3:07 p.m. Very briefly, I have some slides about data because I had a few questions about it last time, and I wanted to point out just a couple things about data entry. Even though I am teaching you, well, let's keep the slide up here, about how to use software to do analyses, if you have to start from scratch in terms of data entry, like you have questionnaires or something like that that are done on paper, you can put that into Excel. And I would say you should put that into Excel. Any Google spreadsheets, whatever, any spreadsheet program where you can clearly see what goes where and you can like freeze panes or split it to look at everything, that's totally fine. Because every software program has the capability of importing an Excel file. So for your homework, I'm giving you Excel files as your data. That way you can click on them and open them and look at them. And you don't need SAS or R to do that. So in the syntax that I'll walk you through in the videos, the hardest part of the process is often telling it where your data file is. Once you get over that hiccup, it's much easier. In terms of information that goes with your data, you would have names, you would have labels, and you would potentially have value labels. So variable names, when you're setting up a spreadsheet for the first time, start with a letter. Do not start with a number. Do not put spaces in there. No special characters other than underscore in a variable name. Otherwise, you're going to have to rename them all when they go into the program. In programs like SPSS, SAS, and Stata, you can also add an element that goes with that column that's known as a variable label. And that is where you can put the details in. So you might have a variable name that's something like test1. And then you write out the description. This is the first time they took this particular instrument, and that's what it means. So short, efficient names paired with extensive labels is a good strategy. Value labels are how you tell it what the numbers mean for categorical variables. And that is something you can do in SPSS, SAS, and Stata, less so in R. But I have a workaround that I'll show you in the videos. In terms of naming things, try to come up with a common stem for any variable that you have multiple instances of. So if you have a questionnaire and you have items 1 to 10, don't name the variables with what the question is about. Name it item 1, name it item 2. Put what it's about in the variable label, because if you want to refer to a series of variables, you can type things like item 1 dash item 10, and it understands that you mean 1, 2, 3, 4, 5, 6, 7. Whereas if they're separate names, you'd have to write them all out. So there's all kinds of shortcuts to the code that you can use if you have things that are named in a systematic order like that. One thing about entering data in Excel, stay away from the conditional formatting. So I get data sets from people that they have notes in them where it's like, well, the cells that are in red mean this, and the cells in yellow mean this, and SAS does not care. That information does not get transferred into a software program to do analyses. So if you want to say this means this means that, you got to find a way to do it in the columns. Question, the $ in the examples. So is the $ the same in R as it is in a dot in SAS? Yes, it is. So both R and SAS have a variable name convention where it's data set and then a divider and then the name, or excuse me, place where it is in SAS and the name of the data set. And then in R, it's actually name of the data set, $ variable. So it's a little bit different, but the $ is a divider of the name in the same way that the dot is in SAS. That was the question. One other thing before we go here, I want to make a point, is if you have missing data, don't put a code for it. Leave it blank. Just leave it, because blank means missing, right? If you try to come up with like -99 means this kind of missing and -98 means that kind of missing, then if it's imported into another program, it may or may not understand that that's what you mean. If you leave it blank, you'll know. If you need to keep track of reasons for missingness, do that as a separate variable. Also, don't write words. So in Excel, if you're entering numeric data and somebody writes down not quite 4, don't put that in your column. Because it will take the entire set of numbers and change it into text instead of numbers. And last but not least, you are allowed to create separate data sets for different levels of analysis. Do not try to put them all into one file because it will create more work for you. So if I have, say, information about teachers and information about students, that's 2 different data files. You can always merge them back together again to do a combined analysis. And last but not least, if you ever find yourself with a data management task where you have to do the same thing over and over and over again to different rows or different columns, send me an email. I once spent 6 weeks as a graduate student doing something by hand that 3 years later I learned was 3 lines of code in SPSS. I once helped a graduate student who'd spent her entire summer doing something manually in Excel that was 4 lines of code. So Excel is for entry is fine, but if you need to manipulate data, the programs are the way to do it. All right. Any questions before we call it a day? I'm going to stop the share for right now here so we can all see each other. Any other questions, I should say? All right. In terms of Thursday, I don't know what's going to happen. The weather is supposed to cooperate, but we got an email yesterday that the internet is being repaired in the north side of the Lindquist Center where our classroom is. So I'm hoping that there is more information forthcoming about whether or not that means we'll have internet, because if we don't, then I can't do the Zoom simultaneously, and that leaves a bunch of you out in the cold. So assuming that we have internet and the weather is cooperating, I hope to be in person on Thursday, but I will send you a confirmation email as soon as I can be certain that that is the case. So I appreciate your flexibility in Zooming up to this point. I do intend to be in person as soon as all of the variables align that would allow me to do so. But you are still welcome to Zoom from home, even if I'm in the classroom for whatever reason you need. All right. Anything else before we call it a day? All right then. 1 minute early. I'm your hero, aren't I? Just kidding. All right. Have a good Tuesday, everybody. Stay warm. See you next time. Thanks for joining us.
Thank you.
Bye, folks.